Thank you, Fred. Ladies and gentlemen, welcome to this webinar on the 10 reasons to do reliability. And of course, there's more than 10 reasons, but we don't want the powers that be or the people we're trying to convince fall asleep halfway through our list. And I often start my conversations with a picture of a catastrophe like this in regard to an airplane crashing, which we were just talking about for those who just joined. Thank you for the context of the crash I was talking about, Michael. And a lot of reliability engineers or motivators, so to speak, start with tales of woe and destruction like this airplane crashing to the ground. And they say, well, because this is what reliability is all about. We're trying to prevent disasters like this. And that is where they stop trying to motivate. Just talk about all the doom and gloom stuff, say everything's going to be very, very bad if you don't listen to me. And then they often start talking about things like how reliability engineering is all about measuring reliability. If you go to a university course, if you go to a university where they do reliability engineering, 99% of the university course is all about measuring or analyzing reliability, coming up with increasingly sophisticated models to describe how things can fail. But unfortunately, it is not nearly as important as designing reliability into your thing. And that happens when we have a reliability mindset. And so what I'm going to talk about today is the 10 reasons to do reliability engineering, where we use the reliability mindset. And what I'm trying to do today is give us the language, or at least some of the ways I've had success in explaining or convincing people to do reliability engineering, that go outside of the statistics. This is the amount of money you save, this is the amount of disasters you'll mitigate, et cetera, et cetera, et cetera. And I want to start by, when I talk about these 10 reasons, I want to talk about the pursuit of happiness. And let me explain. The 10 reasons you can see are on the screen right now. Reliability engineering does not equal reliability purgatory. We're here to eliminate all problems, not just the problems associated with failure. Good reliability involves no complex, expensive fixes. We save lots of time and money. We quickly solve the vital few and not the trivial thousands. We make our things better than our competitors when we take reliability seriously. We generate value. There's no overwhelm. There's happier people, and you enhance your reputation. So let's just go through this from top to bottom, hopefully building upon a narrative which will make you want to tear into reliability engineering when we're done this conversation, or hopefully, and I should say, not just or, allow you to convince those around you that reliability engineering is awesome because it's not equal to reliability purgatory. Now, I often use some of the so-called enemies of reliability in my courses and my presentations, my webinars and my discussions. And here is the first one, the ponderous professor. Now, he usually starts with a picture of an aircraft that has crashed or something similar and say, this is why reliability is very, very, or really, 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 really important. And then he launches into all manners of equations, charts, calculus, PDFs, things like that. And then if he's asked to do anything to help you make better decisions, he always says, I need lots more data and lots more time to answer that question. And the reason being is this guy is a ponderous professor. He represents a set of behaviors which are all too common in reliability engineering, where they would rather have 5 years to get the exact answer, which is usually 4.9 years too late for the decision we're trying to make, as opposed to an informed decision right now. The other thing is that what you can see on the screen is what we call reliability purgatory, where we feel like we're forced to do all these equations and learn all these statistics in order to make a decision. That's simply not the case. All you need to do is first work out what information you need to make a decision, and then work out if you need an equation to make that decision for you. So that's the first reason. Reliability engineering is not reliability purgatory. But the second reason is one of my favorites, because reliability engineering is all about eliminating problems, not just the problems associated with an aircraft crashing into the ground at a great rate of knots. This, of course, is, I suppose, theoretically or philosophically, the main reason we do reliability engineering, where we're trying to prevent failures in the hands of your user or customer. We'll call that problem number one. But there are also so many other problems we're trying to prevent as well. So for example, let's just say you're designing an amazing new thing, amazing new product, and you come across an issue during manufacture. Let's call that problem number 2. Now, fixing that problem during manufacture is very expensive, not nearly as expensive as the plane crashing to the ground. And unfortunately, that usually means, even though it's very expensive, but less expensive than problem number 1, we have this wonderful emotion called hope kick into play, where we often convince ourselves that, hey, you know, this is an anomaly, this is an outlier. We'll fix this during, you know, when we go from low rate production to high rate production, we'll be able to quality control and continually improve. Let's just hope or wish this problem away, which means that very quickly, that problem you could have fixed during manufacture becomes problem number 1 again. The third problem we're trying to eliminate when we do reliability engineering is problem number 3, where we rely on design reviews to uncover problems. Then we go away and design out of our system. A better term for this is build, test, fix, where we build something before we work out if it's going to work or not. And this is slow, expensive product development. We don't want that. Sure, there is a place for build, test, fix, but if that is how you do business, then you're in an organization where it takes a long time to design something. And by the way, because you go through your resources very quickly, you never reach your potential because you have that finite amount of resources in your schedule and budget. So, but that notwithstanding, problem number 3 is still preferable to problem number 2. And of course, problem number 1. It's just that if this is how you go about doing stuff, then you are going to be handcuffed to a slow production process. Then there's problem number 4, where we actually early on try and take parts of our system and, for lack of a better term, break them to see what their weak points are. These are problems that we are actually trying to uncover. We're trying to push our products either to or beyond its operating limits in order to find its weak points, because we design those weak points out of our system. But my favorite problem is problem number 5, where it's never a problem at all because we've thought of it before our first design and we design it out of our first design. So it's never allowed to happen. And so reliability engineering is all about addressing problems 1 through to 5, even though problem number 1 gets the most airplay, so to speak. So let's think about an organization with this young engineer here, and the organization is only aware of problem number 1. That's the only problem that they think reliability engineering addresses. In fact, they think reliability engineering slows down the product development process or otherwise is an embuggerance, and we'll talk about that later on. But if we only think that reliability engineering is there to arrest problem number 1, which it is, but it's a whole lot more than that, then invariably we have our poor old young engineer who is tasked with resolving or trying to take reliability seriously, invariably asks, well, what's the reliability number? How good is good enough? He also knows this is years in the future. He also knows that there's a whole team of people who are building this brand new thing. So it's not just his responsibility, which means that even if he puts in additional time and effort, unless everybody else does the same, you're not going to have the same improvement in reliability. And of course, he's doing the build, test, fix thing, so he's already behind and over budget. He is always told that this is all about brand value and everything else in reliability textbooks, but he doesn't care because he's not a shareholder of the company. He might not get promoted anyway. So it's all about his personal brand. And long story short, this quickly becomes something which he doesn't think is his problem if we only ever focus on problem number 1. And that's, amongst other things, down to the fact that reliability always seems to be a cost. So we have an invoice for reliability without too many benefits. And of course, these costs drive the emotions of our brain, and emotions, not facts, are how most human beings make decisions. And so because we are frustrated with reliability engineering because it's always there to slow us down, we try to downplay it. There's no reward for eliminating problems. Reliability becomes that embuggerance. We test to pass and not test to learn. And our young engineer essentially says, what is the least I have to do? Because if I do anything more than what's the least, then that's resources that I personally lose when it comes to me developing my brand. It means that I might go over budget or take a little bit too long to make my thing reliable. And therefore, my peers who sit in the same office building as me, who don't do those things, they will perceive to be better performers because their monthly or weekly quotas or profit and losses or whatever the right metric is seem better than mine if I take reliability seriously, because reliability only ever comes with an invoice. And so the leaders respond by insisting that if we're going to do anything regarding reliability, even though reliability is our number one priority, you need to give me a business case. A business case is all about measuring and not improving. We often have buckets of gold because we need to justify on what action each dollar is spent. We then often need lots of statistics, and there's never enough data, and our ponderous professor is wheeled out because our leadership team insists that they don't want to have any risk associated with investing what are scant resources into reliability when it's perceived to be only an invoice/cost as opposed to an immediate reward. And so what that means is that all those problem number fives, all of those issues that have the potential to be problems number 5, those ones that we eliminate before our first design, they're going to remain, but they'll become problems 1 through 4. The only difference is that problems 1 through 4 are exactly the same as problem number 5, except we didn't look for them. So that's all well and good, you might say, but how do I get to convince people to stop, take a deep breath, and think about reliability engineering before we start focusing on how it's going to affect our users or customers? Well, that brings me to my third reason, and that is no complex, expensive fixes. Now, for some of the veterans of my webinars, yes, here is my smart lock, one of the centerpieces of my conversations I have with you and students on what seems like a daily basis, probably to you, definitely to me. Now, we know that a smart lock is a wonderful combination of traditional mechanical lock technology and emerging smart technology, and it's a very good proxy for some of the design challenges we have today, regardless if you're working on the F-35 Joint Strike Fighter through to a consumer product, because we have a bunch of not competing technologies, but very different technologies that need to work in perfect harmony. But perhaps the most important part of our smart lock is the electric motor, the thing that makes the lock and unlock. And the electric motor of virtually every smart lock will turn the gears, which we call it a gear set, that then drive that lock, or the bolts, I should say, going in and out of the striker or the hole in the striker plate. And of course, our electric motor doesn't do this by itself. It needs something or someone to control it. And that's where the printable circuit board, PCB, contains all the circuitry where the firmware and everything else is stored so that it can correctly command the electric motor to lock and unlock. And of course, we know this about a smart lock. We know that these things need to be in place even before we start designing our first design. But when we are dealing with cool technology, emerging technology, we often forget about the really simple things, such as the effect that door slams might have on these solder joints, which connect the cables or wires from the PCB to the electric motor. Now, if you're a reliability engineer with any level of experience, you will have come across horror stories of seemingly well-engineered products or devices or machines failing abysmally because of some of the stupidest, dumbest reasons known to engineering. And yes, solder joints that fail is one of those reasons. We often rush to embed smart functionality in things like smart locks and just forget about the basics. So let's think about the effects that door slams have on solder joints. And solder joints are obviously there to allow electricity to be conducted between two different materials, in this case, the electric motor and the cables, and then the cables and the terminals on the PCB. They are there to provide some structural support to keep those conductors in the same place. but they are not particularly strong when it comes to, let's call it, overarching structural support. So if you had these basic solder joints in a smart lock and your smart lock was installed in a door where for whatever reason there was a larger number of door slams than you anticipated, pretty soon these solder joints will come undone, essentially fracture, and you'll have a completely useless smart lock, regardless of how much time, money, and effort you put into all the smart technology. So what can we do to mitigate this clear, well-known problem in the world of consumer electronics? Well, the first thing we could do, and we'll call this a corrective action, is use thicker gauge wire to provide more contact area with the motor terminal. We can use shorter wires that accumulate less momentum during the door slams themselves. Corrective action number 3, use clips to physically secure the wire so their shock loads are transmitted to the chassis and not to the solder joints. Corrective action number 4, use a socket and plug instead of a solder joint in the circuit board, which also makes this thing much easier to assemble. And then corrective action number 5, visual inspection of motor solder joints to be added to the supplier inspection checklist. So you can see straight away that one of those things that we always struggle with is, well, what do we test from our suppliers? If we think about what might go wrong, at the very start, our test regime starts writing itself, and we're focusing on the things that will go wrong versus the things that a standard or textbook says could possibly go wrong in other products. The last corrective action is to do a surveillance automated microscopic optical inspection for 10% of incoming motors to identify any micro flaws that our supplier might be embedding into our sockets. Now, Carl writes that predictive maintenance might help. I would agree in principle, but as a rule, when you're selling consumer electronic products, you're not asking them to do predictive maintenance for you. This is supposed to work until it stops working. But if we go back to these corrective actions, if these are embedded in our first design, they are essentially fast, simple, and free. Now, I know having thicker gauge wire incurs a slight increase in supplier costs. We know that the wire clips obviously are an additional component, which obviously incurs additional costs. But comparing that to the recommended retail price, these are negligible costs for what is a relatively complicated or sophisticated system. So when I say free, they are borderline free because the costs associated with these things are almost imperceptibly small when it comes to your profit loss statement. And now by doing this, we have turned what might be problem number 1 into problem number 5 because we embed these corrective actions into our first design. But of course, then there are things that like the printable circuit board, PCB, which are a little bit more tricky to understand when it comes to reliability. And that is because these things are going to be subjected to vibration during door slams. It's not really apparent or intuitive how that's going to affect our components, because those components are somewhat fragile, as are the connectors, and eventually vibration could ruin the day of our PCB. And let's just say we know that this is a concern, but we don't know initially what we need to do to address it. Then we can use that thing called highly accelerated life testing. I've done a webinar on that in Ascendo. If anyone wants to learn more about that, in a way, all HALT does is try and break components or sub-assemblies by scientifically increasing stresses. And when we find the thing that breaks first, we know that's the weakest point, and we try and design that out of our system. And in this case, when we do HALT, it turns out that this large capacitor easily broke free. But we need that capacitor, so what can we do? Well, we might install some additional rubber mounts to isolate the capacitor from vibration and shock forces. Now, of course, this also incurs a little bit more money, but if we embed these little rubber mounts, which we tend to need anyway, but if we put them near the capacitor, because that's our problem child, then we have turned what will be problem number 1 again into problem number 4. Yes, there is a little cost involved, but realistically, HALT is extraordinarily cheap and very, very fast. And now we have a robust, reliable design. And this has all happened because we took the time to think about what might go wrong in a scientific way. So things like Vermeers and Holtz are wonderful tools to make our first design a reliable design. And every time I show this to intelligent people like you or students, everyone can just see that this is now robust and reliable because we have confidence based on the engineering. Confidence is a measure of you, not of your system. You can get confidence from statistics, which is long, expensive, and sometimes not as reliable as you would like, or you can gain confidence from actually designing robust, reliable products in the first place. But this will never happen if we have a business case mindset where we need to justify every additional delay, every additional expense, where we have to explain how much money we'll recuperate from a Vermeer or a Holt, or adding these little rubber mounts and et cetera, et cetera, et cetera. The key is that we just spend the money anyway because the amounts of money involved are tiny compared to the overall benefits we're going to get. And if you have an organization which understands that, then you're cooking. However, if you need to justify every half-cent increase on the costs during the initial design process, good luck. You're in a lot of trouble. And so then we have, instead of the business case mindset, the reliability mindset. Now, the reliability mindset is all about what we just talked about, having those fast, simple, free fixes or corrective actions. And of course, this will never happen if we have our second enemy of reliability engineering at play, the infant manager, whose favorite phrase is WTF, which stands for, as we all know, I want the wrong thing fast. He is so keen to get to the first milestone or the next milestone as quickly as possible, demonstrate to his boss that he is saving, he is progressing faster and cheaper than anybody else. Therefore, he is awesome, and he will not be open to ideas like genuine Vermeers or genuine Holtz, or just simply allowing the engineering team to sit down and consider what might go wrong, as opposed to working out what will go wrong after you build it and then test it. So as you can see, Carl's written a couple of things. He wrote, or breakdown happens when the warranty runs out. Not entirely sure what that means. Of course, breakdowns, every smart lock's going to fail eventually. Every product's going to fail eventually. A fraction of products will fail in the warranty period. But of course, if things fail in the warranty period, that is a direct cost to us if we have to pay for warranty action. But if things fail after the warranty period, then that has the ability to affect brand and everything else. There are some brands out there that we know just last a lot longer than everything else. And we know that because they have brand reputation. They just last longer than the warranty periods. And there are other components and products which just seem to get through the warranty period and then almost on cue fail. We know what those ones are. And so there is a price you pay when things get through that warranty period and then fail. And Carl then writes, wrong things fast, bad manager. They absolutely are. That is absolutely a bad manager who, without having the courage to say that's what he wants up front, through all his actions and all his meetings, essentially insists that everyone needs to rush to get the wrong thing fast. And that brings me to the next reason you want to do reliability engineering, because you save lots of time and money. So let's look at a case study. And case studies are few and far between in the world of reliability engineering. That is positive case studies, because a lot of the negative case studies are, of course, played out by the NTSB in courts, and the Challenger disasters and Deepwater Horizons and air crash investigations. But it's often hard to find case studies that show how good reliability engineering can be for your bottom line, besides looking at how much those failures cost. And one such case study involves the liquid fuel rocket engine design. Now, if I introduce this chart here where the horizontal line represents how long it takes to design or build or produce something, let's call it the design time or schedule, and the vertical axis represents cost per unit time, if we rush to build and then test and fix, then our initial raw design effort's going to look something like this, where we have that red lump that shows how much money we're spending per day and for how long we're spending it, followed by engineering support, which is essentially all the stuff we need to do to make our thing transportable, make it manufacturable, make it environmentally friendly, comply with emissions, laws and regulations, et cetera. Then we need to certify. And of course, during the whole time, because this is all about build, testing, and fixing, we spend so much of our time eliminating failure modes and mechanisms, which is another way of saying we're fixing preventable problem. And so that is one way of approaching building the design and production of liquid fuel rocket engines. But it was found that if instead we use the reliability mindset, and which involves taking our time initially, taking our time is probably the wrong phrase, we should say being more considered, being more deliberate, being smarter about it, then we take longer and spend more money during our initial raw design effort. But of course, we save so much more money because we don't have to eliminate failure modes and mechanisms. We've already ensured that our thing is manufacturable and complies with standards and everything else during engineering, so we don't need much engineering support. And importantly, certification is a doddle because we've already know through a considered approach where we examine all the weak points of our system, we know how it's going to fail when it eventually does fail. So they're the only things we need to focus on certifying. And so perhaps in this approach, we have spent twice as much money and spent twice as long when on the initial raw design effort when compared to the build, test, fix approach. And that's how the benefit of doing that is that we now have an overall budget, which is 73% smaller, and our schedule has been halved, all because we made our first design a reliable design, all because of that initial raw design effort that our infant manager hates. He will never allow this to happen because that delays him getting his first milestone, and he can't stand that. So that's why this guy is the enemy of one of the enemies of reliability engineering, and why the reliability mindset is absolutely crucial. It comes down to reliability. And if we do this, not only do we reduce the likelihood that our liquid fuel rocket engine is going to fail in the hands of our user or customer, but in this case, it was about 4 times less expensive and 2 times faster to develop, and in addition to being more reliable. Now, many people will say, well, you can choose 2 of 1, reliability, 2, time, 3, budget. Pick 2 of those. You can make it reliable and cheap, but it can't do it quickly. You make it reliable and develop quickly, but it's going to cost a lot of money. Not so, because if you have the reliability mindset, you're all about making problem number 5, turning all those problems into problem number 5 versus problem number 1. And the other reason it saves time and money is because it reliability engineering is all about quickly solving the vital few and not the trivial thousands. Solving the trivial thousands is what we call over-engineering. And we have no place for over-engineering in this day and age, because that makes things too heavy. It means they cost more to produce. They're often too big, which means that it costs a lot of money to ship them and the parts you need to get them, to make them in the first place. And of course, all this contributes to a larger carbon footprint, which is becoming more and more important, especially if you want to sell stuff across the world. Over-engineering is not reliability engineering. It is expensive, it's unnecessary, and it's going to essentially give you a false sense of security when it comes to how reliable your thing is. Here is an example of an over-engineered iPad holder. And yes, this is a real thing. The reason why it gives you a false sense of security is because you spend all your time and money making things twice as strong, or twice as long, or twice as rated, etc., without ever working out what actually is going to make your thing fail. So it's all well and good over-engineering a smart lock, but if you forget about the solder joints, which are a little bit more difficult to over-engineer, then it doesn't matter, because it's still going to fail after 4 or 5 door slams. So over-engineering is not reliability engineering. And because we're spending less time and money not over engineering, because of spending less time and money on our production, because we are making our first design a reliable design, it then allows us to make our products better than our competitors. So I've already talked about problems 1 through to 5. Problem number 1 is a problem in the hands of your user or customer, where it fails, it breaks, catches fire, it crashes into the ground. Problem number 5 is exactly the same as problem number 1. It's just that we designed it out of our first design before it was even allowed to become a thing. And then problems 4 through to 2 are anywhere in between. But problem X is an unrecoverable problem, in that the product you pour your heart and soul into, regardless of how reliable it is or is not, fails to meet your users or customers' expectation. So let's look at an example of how reliability engineering can make our things awesome. And Motorola is a great case study. Here's a two-way radio, perhaps the most dominant form of communication across the world, at least using radio technology. It's very simple. It has this push-to-talk button, which essentially turns this radio receiver into a transmitter. So all you need to do is have one finger or one thumb push this button, and it turns it into a microphone that allows other people to hear the very important things you want to say. But of course, even this really simple thing can be problematic. So one of the biggest customers for Motorola and two-way radios in general are military customers. And they often need to use these radios with big, thick gloves, which has given rise to historical problems with military customers and the push-to-talk button, because these big, thick gloves can sometimes make it hard, I should say, to work out where that button is, how hard to press it, if you're accidentally pressing it when you shouldn't be, when you haven't pressed it hard enough when you think you have, etc., 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 because you lose that tactile feedback that naked skin provides. So big, thick gloves can get in the way of the user experience. And so Motorola, instead of using the typical engineering definition of failure, they defined failure as being the push-to-talk button being difficult to press military gloves. Now, many engineers will roll over in their graves or die a horrible death when you suggest that this should be a definition of failure, because what does difficult mean? It's a very subjective term. And we are drilled from day one that you have to have very definitive, very specific, very measurable requirements, and that includes definitions of failures. And for a lot of the time, that is what you need to do. But if you are willing to go out of your comfort zone a little bit and look at the customer experience in a subjective way and say, look, if the customer's not happy, let's not try and quantify it too much. Let's just talk about a failure which is based on that subjective assessment of whether your customer's happy or not. And when Motorola did this, they conducted a FMEA, and they came up with these wonderful corrective actions, which started with adding a textured area to provide better tactile feel to the push-to-talk button, those little knobs, which made it that much easier for people wearing gloves to understand or feel where the push-to-talk button was. They added a colored ring for better visual differentiation. If you look at the profile of the case, they added what they call tactile locator ramps, where these little ramps at the top and the bottom of the button allowed even a gloved thumb to naturally find where the push-to-talk button was. And they did a review and worked out the optimal activation force and travel for customers wearing gloves. Now, again, we have fast, simple, free corrective actions that are embedded in our first design. If we defined failure in a very subjective way, if we took reliability engineering seriously, and if we don't spend all our time and money fighting fires with the build, test, fix treadmill, or having to pay out exorbitant warranty costs because our thing breaks in the hands of our customers, when we take reliability engineering seriously, we have the time and money to go the next step and make sure our things are better than our competitors. So that's the 6th reason you should do reliability engineering. And all those 6 reasons combine to essentially be summarized by our 7th reason, because reliability engineering generates value. Reliability engineering isn't making you money, then you are doing it wrong. So let's look at another case study. Again, some of you might have come across this one in some of my past conversations. This one is Hewlett-Packard, 1970s Hewlett-Packard. But that said, the lessons we learned from this case study are just as relevant today as they ever have been. Now, Hewlett-Packard is a company, or was a company, sorry, still is a company that has prided itself in the perception of quality and reliability. And then in the late 70s, we had John Young, the then CEO, step up. And when he essentially started leading Hewlett-Packard, he was aware that Hewlett-Packard was promoting this perception of reliability and quality. He was also aware that Hewlett-Packard had received all sorts of industrial certifications and awards just for being reliable and high quality. But he couldn't work out internally where this came from. He couldn't look at a number and say, okay, that's what our reliability is. That's what our quality is. And so he launched an investigation to try and answer that particular question he was struggling with. And when he did that, he launched an investigation which looked at all sorts of things across the organization. One thing in particular is very telling, and that is where Hewlett-Packard's manufacturing resources were being spent. 75% of money allocated to manufacturing was being spent on manufacturing. 25% was being dedicated to fixing defects in the manufacturing process before that product left the factory, let alone how much money was then going to be spent on all the warranty costs associated with the remainder of the defects that our manufacturing process didn't pick up. And no one knew that this amount of money was being spent on defects. Now, people often try and make the differentiation between quality and reliability, and that differentiation can be useful. Quality is usually associated with the percentage of defects you have in your products. Reliability, often people think, is strictly related to design and how you it then gets handed over to the manufacturing team to make the quality product. That should you have a high quality design, or highly reliable design with high quality components, then everything's going to be okay. But in practice, the delineation is never quite as black and white as that. And so there was a considered process at Hewlett-Packard aimed at reducing the amount of money that was being spent on fixing defects. And the key thing about this is that it came from the boss, the leader, the CEO. This wasn't a thought paper that some junior engineer fed up to the highest level. No, this was something which came from the top down, the CEO. And he called it the 10X project. He said, team, this is what we're going to do. He said, over the next 10 years, we're going to reduce our failure rate, which they defined as a percentage of products failing during the warranty period, by a factor of 10. So the vertical axis in this chart represents the failure rate, or how many things are failing during the warranty period. This red line represents a consistent reduction that will result in 10 times a tenfold reduction in failure rate over a period of 10 years. And he knew this was a bold claim, or goal, but he feared that if it was anything less bold, for lack of a better term, it wouldn't have been taken seriously. And over the next 10 years, Hewlett-Packard's failure rate looked like this. You can see that technically they failed to meet the goal, but that's besides the point. They reduced it by a factor of 8, not a factor of 10. But it came down to the cultural things they were trying to change, and it certainly did change. They didn't involve a mass replacement of workers or staff or workforce. It just involved a change in leadership direction. So what did this mean for things like warranty costs, which we are always interested in as a rule? And so let's replace the vertical axis, the failure rate in the vertical axis, with warranty cost in terms of millions of dollars per year. Specifically, hundreds of millions of dollars per year. Now, if the 10X project didn't come into play, this red line represents how much money Hewlett-Packard would have spent per year on warranty costs. This blue line represents how much money they spent per year on warranty costs. And the area between these two tells us that overall, over this 10-year period, they saved $808 million, so almost $1 billion. But that is just the cost associated with reducing problem number one. The other things that Hewlett-Packard identified was that by introducing this 10X project where they focused on quality and reliability, lo and behold, production time reduced by 30%, just like it did for the liquid fuel rocket engine. Not exactly the same amount of money was saved, amount of time was saved, but you can clearly see whether it's a 50% reduction or a 30% reduction, you'll take that. They're able to reduce the recommended retail price of many of their components and products by, in some cases, 16%, because they are spending less time putting out fires during the production process. Maintenance costs of their let's call it desktop computers, which in the 1980s, a desktop computer is very different to what we classify as a desktop computer. Yes, and they were maintained, but because they were failing less often, they spent a lot less money fixing them. And by the third year, they'd already saved about $200 million in terms of inventory costs, I should say, because they didn't need to have nearly as many spare parts or nearly as many spare products to deal with defects during product production and warranty failures. And that was by year 3, $200 million by year 3. So all this adds up to increased market share, improved customer experience, all those things we just talked about. And they're spending less money doing it, which is, again, a key part of reliability engineering. Now, I can see that Carl's written a couple of extra questions or comments. He says that mistakes and breakdowns can be a learning experience as long as they don't cost too much. I would actually challenge that and say mistakes and breakdowns are a learning experience regardless of costs. In fact, some of the more costly mistakes you make are some of the best opportunities to learn. But I take your point. We should always learn as opposed to trying to pass a test. And I think he writes, employee and operator integrity is a key factor in keeping all processes reliable and functional. I'll challenge that one as well, because your workforce, if you look at the case of Hewlett-Packard, the workforce didn't change. They weren't more or less, they didn't have higher or lower levels of integrity as a result of the 10X project. They simply behaved the way the leadership team asked them to behave. They saw the leader, the CEO, taking this seriously, and he took it seriously. He was personally invested in it. And so they realized, well, if the leader takes it seriously, the boss takes it seriously, I need to take it seriously, because if I'm perceived to not be taking it seriously, I'm not going to be doing well when it comes to career progression and salary potential and things like that. And so the entire workforce essentially changed from a cultural perspective due to leadership. It wasn't a huge change in integrity or anything like that. It came from leadership encouraging people to find problems, hunt for failures as early as possible, because they knew it was going to save money in the long run. And that also meant that that workforce, that Hewlett-Packard workforce and every other workforce which takes reliability seriously, is rarely overwhelmed. It's another fear of reliability engineering. So if we look at this sort of very generic, I should say, product development process, where you might start with a concept of something, you might then formalize that concept using specifications, you might design that product or process, manufacturing process. You're then going to build the assembly line for your brand new toilet paper. Then you need to work out how to support that assembly line, and eventually you'll need to dispose of said assembly line, whatever it is that you're focusing on making. Now, with this particular, very generic, let's call it life cycle, you can throw millions of reliability activities every step of the way at your production life cycle. And this is just some of them. Textbooks have so many more reliability activities than these. And of course, the first thing you're supposed to take in from this slide, which you can see on the screen right now, is a feeling of overwhelm. Bad examples of organizations who try and make sure every one of these things happen are military customers, very bureaucratic, corporate-driven organizations who just simply have a never-ending list of things you need to do to ensure things are awesome. And this is because those organizations are dominated by our third enemy of reliability engineering, our process zealot. Now, by this stage, some of you would no doubt be saying, with the ponderous professor, the infant manager, the process zealot, I've met them. I know who that person is. I could walk into their office and they even look the same. And that's because these people are too widespread for good reliability outcomes. And the process zealot is someone who's not interested in you making a good product. They're interested in making sure that you comply with the process. Process zealots aren't particularly good at engineering. And we often see process zealots allowed to flourish when we have, Fred introduced a term in a recent podcast, industrial tourists, where for example, you have a young gun who's fast-tracked for greater things in an organization. And so for their experience, they're going to spend a year or so in charge of manufacturing. And then you need to teach them how to do manufacturing in addition to actually doing manufacturing. And that's a very bad outcome, because then that industrial tourist who is not a strong engineer or manufacturer or technician, the only thing they can or can't contribute to, the only thing they can contribute to is the process, another step. Let's have another checklist. That's the only thing they do. So the only thing they know how to do. And that's where process zealots flourish. But these guys get in the way of good outcomes because a complex process becomes the product. If you look at the US DoD product development process, a product acquisition flowchart, it is like flying over a city. You have to zoom in to see what each one of these little steps is. And when you have a product process that is that complex, complying with that process becomes a measure of success. So the complex process itself becomes a product itself. This is a thing we convince ourselves all we need to do is go through this step by step by step, and we will have a reliable product. Amongst other things, it doesn't work, but it also doesn't attract the people you want. Engineers who want to spend time making wonderful things, or manufacturers who want to spend time manufacturing high quality things. Instead of doing that, they spend 90% of their day compiling their slides into a PowerPoint slide deck in order to convince people who don't know what it is you do that things are okay. And that is always a bad thing. And if we can avoid that, we get happier people. The ninth reason you should do reliability engineering, because that process zealot is not a thing. If this process zealot cannot show why their checklist adds value to the product itself, organizations very quickly get rid of those. I'm aware of a large organization which was very, very agile, very, very focused on good quality products. You know this organization if I was to share the name with you. But anyway, they had issues where they had so-called quality control guys and girls come into their organization. And those quality control guys and girls, the only thing they could do was to comply with standards and comply with checklists. And that's not what the organization was asking. They were asking them to use intuition, use skills to try and improve and continually refine quality in their products and processes. And these quality control guys and girls I was talking about, there's a finite segment, I should say, of the entire quality control industry, but you know who I'm talking about. Those guys and girls had a very rude shock when they were expected to actually help improve things. They were there to assess and critique. That was not well received. And so they have very short careers in the organization I'm talking about. The other reason we have happier people is because when we have reliability engineering actually working well, there is no infant manager who is a very difficult person to work for. And of course, we have no ponderous professors because we don't have 5 years to have a peer-reviewed article in some journal somewhere which gives us the answer 4.9 years after we needed that decision to be made. And so these are the enemies of reliability that if we can eradicate, we have happier people. Instead, we need to select the vital few effective reliability tools that drive high quality and reliability based on the circumstances of the program being supported. And reliability plans that work are those that identify and deploy the right tools for the program. And your enemies of reliability aren't really interested in you doing that. Now, the last reason you should do reliability engineering is because it affects your reputation in a good way. So just imagine that this is you. This lady here represents the consummate professional engineer, technician, manufacturer you want to become. If you can get these first 9 reasons into your way of thinking, get that reliability mindset happening in your organization and around in those around you, then you get reliability designed into products and processes. You have a culture where you know that calculating reliability can be important, but knowing how to make something reliable is way more important. And you need to have these practices integrated into overall product development and design processes. Those practices where we hunt for failures to try and turn them into problem number 5 or perhaps problem number 4, as opposed to design reviews, build, test, fix, problems uncovered during manufacturing, and worst of all, problems that our customers uncover for us. Now, if you don't do this, then essentially your reliability philosophy is based on the reliability fairy who sprinkles reliability onto your product or process after you spent a lot of time and money developing something. That has never once worked. You can't test your way to reliability. It can't just